Alright, in this video we're going to go over how you might actually implement a graph class in C++. So here is an example of some code in main that might call a particular implementation of a graph class. So here you can see that we have a templated graph that takes in two different types, as well as a constructor that takes in a parameter. So how might this be set up? Adjacency matrix, adjacency list. It could be either. We can see here that the types associated with each of these declarations here is first the vertex type, and then second is the weight. So we're using strings to represent each vertex, and then we're using integers to represent each weight. The parameter passed in here, you can see, is going to pass in the number of vertices. And then we would maybe have a bunch of functions that could then build the graph. So we would have functions that could add nodes and vertices, and then we could have a function that adds the edge. If we want to add an edge, we know that we're going to need to receive information about the source and the destination of the nodes that are involved, as well as the weight of the edge as well. Now, how these actually work behind the scenes would be dependent on whatever representation that we choose, as well as whatever abstractions we use to represent that graph. So let's think about maybe adding to this graph class and what this might look like. Let's say that we wanted to calculate or determine the neighbors of a particular vertex. So neighbors are all the vertices that are adjacent to the node that you're looking at. So adjacent is defined as reachable via a single edge. So we want to be able to determine a set of neighbors associated with a particular vertice. So let's do an example. So what would be the neighbors associated with B? Well, they are reachable by an edge, so we're only going to look at reachable from that edge. So we know we can get to A, we know we can get to C, and we know we can get to D from vertex B. How about vertex C? Well, from vertex C we can only get to E, so that would be the list of neighbors for C. And then let's look at F. So F doesn't have any, so whatever we had would need to be empty for F. So that's what we're looking to add to our class, is a neighbors function. So the question is, if you were going to write this neighbors function, what would you use here as your type to return this collection of neighbors? So the options listed here are a pointer to a dynamically allocated C array, a vector, a queue, a map, or a set. A vector is a good option because you could iterate through the vector and be able to see all the neighbors that are associated with that vertex. And you could also use a set. The set would allow you to iterate through the list of neighbors, but it wouldn't have order associated with it, which in many cases isn't necessary in order to be able to navigate through a graph. As you just look at a particular graph, you can see for yourself that there isn't necessarily any advantage or anything you would want to know about the order of going to B or going to D, right? Maybe you could want to sort it by some way like weight or alphabetical or something, but it wouldn't necessarily be necessary in all implementations of a graph. So either would work. A pointer to a dynamically allocated array could work, but why, right? If you have the abstractions that are much more convenient to use and handle their own memory, there's really no advantage to using it in this particular case. A queue is a little bit too restrictive because you only have access through the front of the queue, and it's not really good abstraction for this particular case because you probably want to iterate through the neighbors, and so there would be no advantage to using a queue. And then a map is also not necessary because we don't really have any way of getting better information about our neighbors. In most cases, a map would not help us. Maps are used for being able to look up quicker, but we don't really have any way to look up the neighbors in any convenient way. So in most cases, we just want to try them all, for example. Another thing to think about with the implementation of the graph, and we hinted at this last time, was how do we know that, for example, O'Hare is the first one listed on the row and column list. So in the matrix, whether you're talking about source and destination, how do we know O'Hare is the first one, and how do we know that Dallas-Fort Worth is the last one? Well, generally speaking, we're talking about how would we know. You could imagine lots of ways for this particular graph, like you could store them alphabetically, or you could store them in some other way that they're inserted, or something like that, right? You could choose that, but we want to do it efficiently. So what data structure could we use to find a particular vertex in either a adjacency matrix or an adjacency map? Should we use a map or a balanced tree? Should we use a hash map or a hash table? Should we just use a vector and keep it sorted? As I said, just like keep them in alphabetical order. Well, any of them would work, and as you know, they all have different complexity. I think most people could understand that they could probably come up with a hash function that could hash a particular node string to a index in the adjacency matrix. That would be something that you could do pretty easily with lots of different nodes, and then that could be an O1 operation, or you could keep track of them in just some sort of map or balanced tree. So then we would have some like log n complexity associated with finding a particular vertex and its edges. And then same with a vector. If we kept it sorted, then we could use binary search to also do log n. So they're all good solutions. Obviously, hashing would be the most efficient solution, so if you can come up with a good hash function that could avoid collisions or avoid a lot of collisions, then that's probably your best option for efficiency in the graph. So in general, writing a graph class all depends on what you end up choosing as the data structure or the abstractions to build the class, and that's where all the interesting stuff happens. So you can build graphs in lots of different ways. We've talked about the two representations, the matrix or the adjacency list, but even within those, there's lots of choices to be made on how you do things. So matrix is pretty straightforward. You're just going to have this n by n matrix, but then you have to choose, well, how do you actually know that O'Hare is on 1 and Dallas-Fort Worth is on 3, right? Well, that's another data structure abstraction that you get to play around with. Same with the adjacency list. The adjacency list leaves lots of options for data structures and abstractions to actually implement. The same issue is still true when you have this first list here, whether that's a vector or a map or anything. How do you know which one is where? And then once you get to one of those, what kind of abstraction do you have off of that? Do you have a set? Do you have another map? Do you have a vector? Lots of different options there. And all of that goes into the private section of a graph class when you're implementing it. The behavior of the graph is as expected. You set up a graph, maybe you initialize it to some number of vertices or nodes, and then you have functions like add vertex, add edge. The person who is using your graph class, yourself included, doesn't want to have to worry about what's under the hood of the graph class when they're using it. So when you write all of those public functions, you want those to be independent of which abstractions and data structures you use. Okay, that is it for the graph class.